Hello, my name is Sasha and I'm an undergraduate chemistry student at McGill. This summer, the CREATE co-rec program gave me the opportunity to pursue a collaborative corrosion project with Dr. Janine Mazeral in the Department of Chemistry at McGill and Dr. Ed Aslan in the Department of Materials Engineering at UBC. I would like to begin by acknowledging that my research in Montreal and in Vancouver took place on unceded Indigenous lands. The Ganyan-Gahaga Nation is recognized as the custodians of the lands and waters in what is now referred to as Montreal, while the UBC Vancouver campus is situated on the traditional lands of the Musqueam First Nation. Science is often considered to be a rigorous, systematic, and evidence-based method that produces objective results. However, it is important to keep in mind that our research is supported by academic institutions and industrial partners that often have colonial roots, as well as their own current-day values in mind. These often conflict with Indigenous interests. Therefore, for a research program such as COREC that is interested in working on Indigenous projects, it is important to keep in mind the value-based nature of our research and to work directly with Indigenous peoples on projects that prioritize Indigenous interests. This is something that I will keep in mind in the future. Now, corrosion is a phenomenon that impacts everyone. According to the 2016 impact study by the National Association of Corrosion Engineers, the global cost of corrosion is estimated to be $2.5 trillion, equivalent to 3.4% of the global GDP. By using available corrosion control practices, it is estimated that savings of between 15 and 35% of the total cost of corrosion could be realized. In addition to this overwhelming financial burden, corrosion also has major consequences on the environment and human safety. One manifestation of corrosion involves the deterioration of industrial metal structures in the atmosphere. An improved understanding of the corrosion rates of these metals is necessary in order to take the appropriate preventative measures to mitigate the damage caused by corrosion. The corrosion rates of different metals will be different in different atmospheric conditions, depending on factors such as temperature, humidity, rainfall, and pollutant levels. While there are various laboratory methods that seek to examine the atmospheric corrosion properties of metals, these are not representative of real atmospheric conditions. In a country like Canada, with widely ranging climates, it is of interest to be able to monitor and compare the real atmospheric corrosion rates of metals across different regions, and to determine any correlations with environmental conditions. A standard method for monitoring atmospheric corrosion involves exposing metal coupons in the atmosphere and measuring the change in mass over time due to the formation of corrosion products. However, this method is both time-consuming and does not allow for the collection of any real-time data about corrosion rates. An alternative method involves measuring the galvanic current between a noble metal and the corroding metal of interest. This current is directly related to the corrosion rate. As such, this method has the potential to be used in a portable sensor that will collect real-time data about corrosion rates in varying atmospheric conditions across Canada.
My electrode setup for a galvanic current-based corrosion sensor involves a gold cathode and a galvanized steel anode. The gold is deposited on a thin film of PTFE that acts as an insulating layer between the gold and the galvanized steel. Slots in the gold electrode allow for an aqueous layer to connect the two electrodes. Then the galvanic current is measured between them. My mobility to UBC allowed me to utilize the materials engineering machine shop to carefully machine pieces for my electrode setup, and also to use the salt spray chamber in Dr. Aslan's corrosion lab to perform preliminary tests.
Altogether, the COREC program gave me the invaluable experience of working through various stages of a research project as an undergraduate student. From an extensive literature search to collaborating with professors, research assistants, and graduate students at 2 different institutions, to designing and implementing my own experimental setup, there were many different aspects of this project to learn from. Perhaps one of my favorite moments was when Dr. Aslan told me what he often tells his students: "You're an engineer, so engineer something." As a chemistry student, this was not in my comfort zone, so it was a new and exciting experience for me. While focused on my own project, I was also intrigued by the interdisciplinarity of corrosion studies during my time working with electrochemists at McGill and with materials engineers at UBC. Now I have various diverse experiences to pull from when I consider my future as a scientist.